From the studios of Foxboro Cable Access, located in the center of Foxborough, Massachusetts, you are watching Around Foxborough.
Hi, I'm your host, Tim Green, tonight, and we have with us a very special guest, Dr. Randall Smith. How are you?
Doing very well. Thanks for having me.
Doctor, do you mind explaining exactly what you do and where you do it?
Certainly. My actual day job and my title is Associate Director for Science at the Center for Astrophysics, Harvard and Smithsonian. It's a very long-winded title to say that I'm really an astronomer. I focus mostly on doing astronomy with X-rays. X-rays are just a type of light, but they're a type of light that, as you know, goes straight through you very easily. And we use that property in astronomy to look through things as well. We use them to basically take fingerprints of parts of the galaxy that we couldn't otherwise see. Also, X-rays, it turns out, are really good diagnostics of really energetic, very explosive events. And so we use them to study a lot of the more dramatic events in the sky. And that's sort of what I got my start doing.
Okay, we were talking earlier about maybe a star blowing up or something like that. That's what you guys are using to measure those kinds of things? We
do. We use, when a star goes supernova and then the resulting blast wave that comes out, all of those generate a huge amount of X-rays. And we definitely use that kind of thing. We can also use them to, if you have, say, two neutron stars that orbiting each other, those when they collide, now a neutron star is a dead star. It's actually like 10 kilometers across, 14 kilometers across. So, you know, the size of Boston. But you can get two of them in orbit around each other. When they collide, they explode as well. Turns out, actually, interestingly enough, we only fairly recently discovered that that's probably where a lot of the really heavy metals come from. So the gold in your and I's rings probably came from the collision of two neutron stars.
Wow.
Yeah.
What else do you guys do at the center there? We
cover basically all of astronomy. We're probably the biggest astronomy center in the entire world because we've got the Harvard Astronomy Department combined with the Smithsonian, which does a huge range of astronomy. So we do everything from studying cosmology and the birth of the universe to things closer at home within our galaxy. We have a large group studying the sun and what the sun is doing. And very recently, we've had a group that launched a satellite, an instrument that called TEMPO, which is actually observing the Earth itself. We're using some of the same techniques we learned looking up to look down and study the Earth's atmosphere. So if you go to our website, tempo.si.edu, you can find the data from that satellite, which is all of the pollutants in the atmosphere on an area by area map. So you can put in Foxborough and get where the nitrogen dioxide is in the air as a function of time. So if you wanted to know when it would be good to go out for a run, when the smog is low, you can map it out now.
Okay. Is there anything that maybe somebody with a home telescope or something like that that you guys would suggest? Yeah.
Well, right now, the biggest thing in the sky has got to be the comet, which has some long name. Don't worry about it. It's the comet next to Venus. You can only see it sort of in the early evenings. But if you look up at Venus, which is going to be in the southwestern portion of the sky, now you can't miss Venus. It's going to be the brightest thing in the sky, and it's going to be the only thing in the sky at around, I saw it tonight, around 6:30. If you look to the right of Venus, you'll see something that looks a bit like a paint smudge. It's not particularly close to Venus, but it's not that far either. You're still looking southwest. And if you're looking for an inverse paint smudge that looks like the dot of the smudge or the drip is at the top instead of being at the bottom, and that's the tip of the comet, and then the tail is going down from there. But it's hard to miss, and even with an iPhone. I've got some pictures that you can see from a colleague of mine, Igor Chiligarin, and he can see it with just an iPhone.
Wow.
Just taking a picture, piece of cake.
Right.
Look soon though, because it's going to be getting sort of harder and harder to see. So by November, it's going to be really hard to see. So,
so look now.
Get on it now.
Okay. You were talking about taking a picture with your iPhone. You and I were talking off camera a little bit about the Aurora Borealis.
Yes.
And that going over and taking the picture with your phone and saying, wow, look at how come now, why is that?
That's actually because of a couple of things. One is the sensors in your iPhone or your just any digital camera are much better at certain things than the human eye. The human eye takes pictures really quickly, much less than 1/10 of a second, and then processes them. And so you don't collect a lot of light over a long period of time. Whereas any kind of digital camera these days will look at something and go, "Whoa, that's sort of faint. I'm going to stare at that for like half a second or a second."
Okay.
My camera, my phone, for example, when I do it, if I'm looking at something faint, it will automatically go into a mode where it takes like 5 minutes to make, or not 5 minutes, 5 seconds to take a photo.
Yep.
With that amount of time, it really gets more sensitive. Also, the CCDs that are in phones these days are actually better at the kind of colors that are in Aurora than the human eye.
Okay.
The human eye, as you might have, could probably guess, is really adapted to work really best for yellow light.
Oh, okay.
But the red colors at the further red
Yep.
don't work as well. Why yellow? Well, because that's what the color of the sun is.
Right.
So, but reds are a little bit harder.
Okay.
So that's where it's coming from. That's why it looks better. But it's definitely been a great season for Aurora, and it could continue. We are at the peak of solar activity. The sun goes through an 11-year cycle. And right now we're at the peak. It's not going to be back to this. So, I think they just called the peak literally like 2 weeks ago.
Wow.
The peaks are pretty broad. So you've got, a 6-month window on either side of it where the aurora could be pretty impressive. And after that, the sunspots and the storms that create the aurora will go away, or at least drop down dramatically. So now is the time to look between now and the next 3 to 6 months. And after that, it might happen once or twice, but not very often until you got to wait another 11 years.
Okay. And we weren't, I guess, in Foxborough, but north of us was in the path of totality in the last eclipse.
Absolutely. It was I gotta say, astronomers have been going the extra mile of late. We've got a comet.
You guys have a lot of work on your hands.
That's right. Arranging these things is no easy feat.
No.
So you can't arrange any of these things. These are all sheer luck, just to be clear. But yeah, the eclipse, the path of totality was just a little bit north of here. I was actually in Texas to see it because it was predicted to have the fewest clouds there, and it was predicted to be clouded out up in Vermont and so on. As it always turns out this way, Texas was actually sort of cloudy, but Vermont was completely clear. It was amazing. But yeah, no, we had a beautiful eclipse. One of the things actually we do at the Center for Astrophysics is we have a woman, Jenna Samra, who has been building a device to measure the eclipse from a Gulfstream jet.
Wow.
So it turns out
and follow it as...
And they follow the eclipse.
Wow.
So she gets to go, she and her team...
It's a good gig.
Exactly.
Yeah.
Built this particular... Now, the tricky part is, of course, the jet is jiggling around a lot.
Yep.
And the sun is staying stable. So you need to get something that will keep the camera smack dab on the center of the eclipse so that you can measure the corona around the sun. So all the gas and all the stuff that is not visible except during the eclipse is what she wanted to measure. So she had to somehow get it to stay stabilized against the eclipse, which the technology she used worked really quite well. She got some great data, and she got. If it turns out that if you cheat that way, if you take a plane to do this, you can stretch what would be an eclipse for 4 minutes or so on the ground to something more like 7 or 8 minutes from the plane. And so they were able to get a really long eclipse.
What kind of data are they looking for when they do something like that?
They're trying to get optical data. So this is ions that are emitting hard to detect lines or diagnostics, basically, of the hot gas that's surrounding the sun. Okay. One of the puzzles that we have about the sun is sort of temperature related. And the easiest way to think about it is the sun is yellow hot. It's not red hot, it's not blue hot, it's yellow hot. That's actually a temperature. It turns out to be about 6,000 degrees. Outer space is basically zero, give or take. In between that, most of the time, you and I would think, okay, well, if this part is 6,000 degrees and this part is zero, then the stuff like around that should be like 3,000 degrees or something like that. Well, it turns out the stuff around it is like 1,000,000 degrees. And exactly, you're questioning it.
Yeah.
It is a puzzle to this day. We know it's got something to do with magnetic fields. And we also know that those magnetic fields are responsible for that 11-year cycle I was talking about. So somehow the magnetic fields are churning around, breaking and moving around. And when they do that, they heat up the gas that's on the outskirts. But what we would really love to be able to do is to measure the properties of that gas as well as we can, as often as we can. And it turns out that's hard to do when you get the whole sun being really bright in your face.
Right.
You know, it's like, you're driving down and you've got at night and there's a car with lights in your face and there's a bicyclist and you know the bicyclist is somewhere there. And you know it's sort of important to figure out where they are, but you got blinders in your eyes, you can't see. So we use the eclipse in this case is a natural way of blocking out the main light so that we can understand what's going on and hopefully understand what's going on. How did that gas get so hot and what keeps it hot? Because it's also, bringing this whole thing full circle, that hot gas and those magnetic fields out there are the things that are creating the particles that then go streaming out into space, hitting the Earth and creating the aurora borealis. So the aurora actually are connected to the same process that is creating the corona around the sun, and it's all tied in with this magnetic field that we don't fully understand.
Right.
So.
I know that in the news there's been some talk of like solar flares and things like that. Does that have any effect on like electronics and things like that?
It absolutely does. The solar flares have it's a multi-step process. So the flare itself is usually due to the magnetic fields getting twisted up something awful. And we can now measure that. We actually are mapping the sun 24 hours a day, 7 days a week. We have data coming down all the time. So we know exactly where these wrap-ups are coming. And we can even tell now when one is looking suspicious, What we then do is you can see one when it sort of snaps, essentially, and sends out a burst of stuff to us. And we've got what amounts to a first line of defense, actually, between, it's a very special orbit between the Earth and the sun called the first Lagrange point, L1. And we have a bunch of satellites that are just basically planted there all the time, and they're measuring the gas and the stuff coming at us. So we get another warning of like, hey, it's really heading for us. But this is real matter. I mean, it's not. I mean, it's gas, and but it's streaming at high speed. The amount of mass we're talking about is significantly more than the amount of matter in like Mount Everest. So it's a lot of stuff. And all of that is coming. It can be coming straight at the Earth, and it's highly charged. It's got lots of energy. It can take out satellites. So when one of these events happens, so for example, the Center for Astrophysics actually runs a couple of satellites for NASA. All the satellites get turned off. We just go into what's called safe mode to say, okay, we're just going to ride this one out, batten down the hatches, and let's stay safe. And then we'll hit the Earth. Now, for the most part, all we see then is the aurora, and it's pretty, and everybody enjoys it. There have been more dramatic versions of this. There was something called the Carrington event back in the 1850s, I believe, mid-1800s. That was one of the first one of these that was ever seen. It was a huge, huge event. It was so big at the time, they didn't have satellites, but they did have the telegraph machines. And the telegraphs required power in order to send the signal. This particular burst came in, it was so strong that in some cases, the telegraph machines, operators' huts blew up.
Wow.
And in other cases, they were able to disconnect the batteries and run without batteries for days because the thing charged up the system so much. Now, if one of those hit us now, it would take out most of our subsystems, our electrical subsystems. That's why it's so important to measure these things and know that they're happening in advance, because if a big one hit, and we'll know, we're able to turn everything off on short notice.
Okay. So that's the idea behind monitoring all these things.
Absolutely, yeah. A lot of this is just protective. I mean, something like that would actually affect life on Earth here, at least but in terms of like our electrical systems, extremely rare, 1 in 100 years. The kind where it's a good idea to turn your satellites off, during times like now, those happen maybe a few times a year at least.
Wow.
So that's actually fairly common, and a good reason to know what the sun is doing, because it can actually affect us quite a bit.
Yeah, I can imagine. Is for like kids, maybe younger kids and stuff like that want to get involved. I mean, everything you're talking about sounds, way up here. Is there a good way for like maybe some of the younger kids to?
Oh man, well, there's certainly lots of great stuff that you can do. Honestly, these days, I mean, you heard the stories about like Galileo built the first telescope and was looking at Jupiter and the planets and so on, and making major discoveries. Nowadays, a decent pair of binoculars is actually more powerful than anything Galileo ever dreamed of. And the wonder in a kid's eyes, looking at Jupiter. Have you ever looked at Jupiter with a...
I think when I was like you said, just a young kid.
Because you can look at Jupiter and there are 4 moons going around it.
I don't remember kids. Yeah, I don't think I did then.
Then maybe you missed that.
Yeah.
With a pair of binoculars on a tripod so it's stable, you can see the moons easily enough.
Wow.
Now that is really cool because you look at this thing that you see as a dot and then you realize there's like 4 things in a line around it. That's pretty cool. Now you really want to blow their mind. You go back like an hour later and you look at it again, or maybe the next night, the moons have moved because the moons are orbiting Jupiter.
Right.
Which, if you think about it, that was the first proof that anybody had that things orbited other things.
Right.
I mean, Galileo looked at that and said, wow, those things got to be orbiting Jupiter. But the theory at the time was that everything orbited the Earth.
Right.
So it was this immediate disproof of the idea that everything had to orbit the Earth, because now you could see it with your naked eye.
Right.
Or rather, through a... So that's the kind of thing that I find just amazing. Now, the other one that's great to see is to see the... even with a pair of binoculars, you can see the rings of Saturn, which, by the way, are going to be going away temporarily because actually it turns out the rings, as you might imagine, are, so eventually they're going to point straight at us. And so you won't be able to see them for a little while until it turns again. So it's coming back. But those 2 I find are really great little gateways.
To get kids involved.
Get kids involved and just to see it. Or to, take a good look at the moon, because the moon is just, you can see all of these craters and you can tell the difference between the old ones that have sort of weathered away a little bit and the younger ones where you can still see all of the details.
Yeah.
Just amazing things to see looking at the moon. So all of these are great. You don't need a whole lot of fancy anythings,
right?
To
like an amateur level telescope.
Easily, not even like I said, a pair of sports binoculars are going to do just fine.
Is there I know obviously we have all the light pollution around here and things like that. Is there anywhere you suggest, like close by, within a couple hour drive?
Yeah, I find going up north is the easiest because once you hit the halfway up New Hampshire or Vermont, you're far enough away that you can get away from everything. Although I've gone out to the Berkshires and had good luck there as well. The truly amazing stuff to see are things like to see the Milky Way, the way the because if you're in the right place to see the Milky Way where it's really, really dark, it goes from being something that people talk about like, oh, that's the Milky Way galaxy, that's what we live in, to like, oh, that big obvious streak of light in the sky is what you see. Unfortunately, unless you go to the like Arizona or something like that, you're out of luck here.
Out of luck. Okay.
Yeah, it's just the Northeast is a great place to live, but it's not great for doing astronomy anymore.
We have a lot of people.
We do.
Yeah,
we do.
Is there anything else you wanted to talk about while being here, or about the center, or?
The center is great. We have at least a yearly tour called Cambridge Explores the Universe, which we just had. So that'll be coming up again in about 11 months.
Okay.
But so put that on your future calendars. The other one that I think I have a slide for is an upcoming talk that people might like on a star called T Corona Borealis, or T Cor Bor is how astronomers would call it. And T Cor Bor is actually a binary star. It's one sort of regular, normal star like our sun, and one star that's sort of dead. It's what we call a white dwarf. And a white dwarf is a star like our sun, but much, much older. And it's about the size of the Earth. It has the mass of the sun. So it's sort of like the leftover core of a star. Well, it has a huge gravity, and it's pulling stuff off of its companion star. So it's pulling hydrogen off of our companion star. And we know that about every 80 years, it goes boom. Because it turns out that if you take hydrogen and you compress it enough, you basically make a hydrogen bomb. Well, this star is naturally doing that. And so what you're ending up with is something that's an Earth-sized hydrogen bomb. And it's going off sometime in the next, I don't know, it could go off tomorrow, but in all likelihood, we're talking about like anywhere from 3 to 6 months. When it does, it's near enough that it is going to be visible in the sky. So you'll be able to see, I mean, it's not going to affect the Earth in any way. It's far enough away that it doesn't have any effect. But you will be able to see something the size of the Earth exploding because it's literally a hydrogen bomb. And we have a talk coming up designed for the public to explain where to go look for it, what's going on, what the physics is behind it. So it should be suitable for kids as well, at least kids who like explosions, which is pretty much all kids.
Yeah.
And so I think I have a slide to show as with the Zoom link and everything. So everybody is welcome to come.
Oh, you can get it on Zoom as well.
You can get it on Zoom, so you don't have to come in person. As a matter of fact, actually, we're just going to do it on Zoom. It's just because we had a bunch of people asking about it, and so we thought, okay, well, we should do an explainer for people and let them know what's going on.
That's cool. Wow.
So
awesome. I think I already asked you about the kids getting involved and things like that. Do you want to talk about a little more about like and again, you specialize in X-rays and things like that. Do you want to talk about maybe some of the interesting things that you were doing with that?
Sure. So at the observatory, we actually run the Chandra X-ray Center, which operates the Chandra X-ray telescope, which is in orbit around the Earth right now. It's the X-ray version of the Hubble, or the X-ray version of the James Webb Space Telescope, the more recently launched one. And we're doing amazing things with it. It's been up there for 25 years and working beautifully. So we've got this great X-ray telescope. It has exquisite X-ray eyes. It can make the sharpest images of things in the sky. And what we're now doing is some interesting stuff where we say combine data from the James Webb Space Telescope with the Chandra X-ray telescope. So we're combining infrared and X-ray data. And one thing we recently discovered is that if you look at galaxies far, far away, these are galaxies that are being formed right after the birth of the universe. So these are like 500 million years old, really, really young. Well, if we look at today's galaxies, we know that most of them have supermassive black holes in their cores, these giant black holes. And we have ideas as to why they do, but there is variation. So for example, our galaxy, the Milky Way galaxy, has a fairly small galaxy in the center of it. Other galaxies have much bigger ones. It seems to go scaling with the size of the galaxy, although not perfectly. But it is the case that usually the mass of the galaxy is a lot more than the mass of the black hole. So when I say a lot more, I mean it's like a factor of 300 to 1 or something like that. The galaxy is much bigger. But what we've been able to do, because with the X-rays we can measure the black holes. Like I said, X-rays are really good at looking at things that are energetic or dramatic, and so black holes are great for X-rays. And the James Webb infrared telescopes is huge and really excellent, and it is good for looking at the galaxies. And what we can find out is that instead of being 300 to 1 that we see here today, it's more like almost 1 to 1 or 10 to 1.
Wow.
And so it's telling us something about how these black holes and these galaxies evolved that we didn't know. I mean, the James Webb Space Telescope is telling us that these galaxies formed much earlier than we ever thought they did. And now we're finding out that their black holes were much bigger than we ever thought they were to begin with. What's going on? I don't know. There's probably a really smart postdoc or a graduate student or some kid who gets interested in astronomy who will figure it out in another 10 years.
Right. Now, a telescope like that, you said, launched 25 years ago?
It did.
Does that have a lifespan?
It has a starting lifespan.
Okay.
It was started at 5 years, was what it was designed to last for.
Okay.
And then it just kept going. As you might expect, the engineers, build things to last. And the team that's running it is trying to make sure that it lasts as well. It's certainly aging. If you've seen satellites, you've probably seen that they're wrapped in this tinfoil-like stuff. And that's to keep the, actually it's to keep the solar wind, the same particles that we were talking about, they'll also affect satellites, and so you wrap them in this mylar in order to keep that off. Well, the mylar degrades over time. Basically, the solar wind degrades it. So as it happens, basically now, what used to be a very easy telescope to manage in terms of pointing has gotten more challenging, because now you have to sort of keep it cold and keep moving it around. It's not an impossible task, it just requires a bit more planning.
Okay.
And so they've been good at doing that, and that's been keeping it alive for 25 years, and we don't know how long it's going to last, but we're hoping to keep it up for at least another 5-10 years.
5-10 years, as long as you can, right?
As long as we can, because you can't get the data any other way.
Right.
This is a unique resource, and we are really happy to be able to have it, because when you use it, especially in combination with other things, you can learn things that otherwise we would never know.
Do you guys launch telescopes recently, consistently, or is it?
We do it fairly frequently. We
Yeah.
have a one we just launched, an instrument on a satellite called Tempo. I think I mentioned earlier.
Yes.
Yeah.
Yep.
And let's see, what was the other? We actually just had, we also do sounding rocket launches. Now, sounding rockets are rockets that just go up and they're above the Earth's atmosphere for about 5 minutes, and then they fall back down. Quick aside on that one. Sounding rockets got their start actually after World War II, when the Allies captured a whole bunch of German V-2 rockets. Turns out there's no real good way to get rid of a V-2 rocket, no safe way, except to just basically set it off.
Send it, wow.
So, I mean, because you don't want to be taking it apart, the thing will explode. So what the Army did, and Air Force has said, okay, we got these rockets, we're going to have to set them off anyway, so scientists, if you come up with some good ideas, we'll put a payload on there. So since then, we have been launching these things called sounding rockets, and it's a great way to test new things. So we actually just had a launch out of Alaska of a couple of new satellites, rockets, or payloads on these rockets. You only get 5 minutes of data, but you can prove out new concepts. You can show that some new technique works. So for example, I wouldn't suggest doing this for very long, but if you point your phone at the sun briefly, you'll see a line form on it, because basically the sun is so bright it overwhelms the camera, and it basically starts, you start seeing some of the internal effects of the camera. And that line is one of them. It's how the CCD is read out.
Yep.
There are other ways of reading out CCDs that can handle really bright sources. And so one of the things that we want to be able to do is to look at some of these places where the storms start, where the magnetic fields get all tangled up, which can get very bright. But we don't want it to oversaturate and become invisible to us. So we have a new kind of detector. We just launched one 3-4 months ago to do exactly that and test that. So that's the kind of stuff we're doing. Now we've proven that works. Now we're working on the next thing, and maybe go to a satellite that would be going up and observing that all the time.
Okay, and then like just proof of concept and things like that.
Exactly, yeah. You can get, actually, we have built one of the very best X-ray telescope on a sounding rocket, and we launched that too. It took some of the very best images of the sun that you could possibly make. And so that one, actually, the science there has actually been interesting all by itself. That's hard to do in 5 minutes, but you can still, there are still places where if you build a good enough telescope, you can do something in 5 minutes that couldn't have been done any other way.
Wow.
So.
All right, well, Dr. Randall, thank you so much for coming in tonight. That was unbelievably informative.
Absolutely, happy to do it. Really.
All right, thank you so much. Yeah,
thank you.
You too. So this was Around Foxborough, and I'm your host, Tim Green, and I hope you enjoyed tonight's program. Thank you so much for watching.